All right, so now we're going to talk about quantum numbers. You'll see that they tie into what we've been talking about already. I'll tell you the punchline here is that we're going to be able to, by the end of it, use a 4-digit quantum number that will uniquely identify any one of those electrons on those orbital diagrams that we've been drawing. So that's kind of what we're working up to, but let's start from the base here. Okay. So as we saw when we did this diagram, when we were doing our diagrams, we saw that we had 2 electrons that would live in a particular sublevel, okay? So we've been able to, we can uniquely identify an atomic orbital sublevel using 3 quantum numbers. N is the principal quantum number. L is what's called the angular momentum quantum number, and M sub L is what's called the magnetic quantum number. This one is going to be brand new to us. The other 2 we've actually already been using and we haven't really been talking about it, right? So if I were to say a 2p orbital, the 2, actually move this here. The 2 would correspond to the principal quantum number. The p would correspond to that angular momentum quantum number. Why is it called the angular momentum quantum number? Very complicated reason. How we think about it is shape, okay? Just like we were saying with the principal quantum number, that 2, we think of as being related to size, okay? Magnetic quantum number is kind of the new one, and we'll talk about that here in a second. So again, principal quantum number, N, is indicative of the relative size of these orbitals. So down below we have 3 different s orbitals that differ by their principal quantum numbers. So we have the 1s, which is the small sphere, the 2s is a little bit bigger of a sphere, and the 3s is now an even bigger sphere, okay? 4s would be even bigger, 5s even bigger, right? So that those 1, 2, 3, those are the principal quantum numbers. You'll note that, like, as we get bigger and bigger, we have more what are called nodes. It's a little bit more beyond what we need to know for this class, but basically these are these magical regions that electrons can't be in. So an electron can be in this region, this region, and this region, but somehow gets between them without crossing through the middle there. It's one of these magical properties of the quantum mechanical world. Let's not worry too much about that, okay? So anyway, that's this principal quantum number. We've already been dealing with that. L is this angular momentum quantum number, all right? It corresponds to the relative shape of the orbital. What's going to be a little bit different here than what we've been doing is we've been referring to these atomic orbitals by these letters, S, P, D, F. Those are the common ways to do it. However, when we're talking about quantum numbers, there's a corresponding number that would go with it, okay? So when we're talking about an s orbital, that corresponds to a quantum number of L equals to 0, right? L is this angular momentum quantum number. If we're talking about a peanut-shaped p orbital, that corresponds to a value of L equals 1. A d orbital, L equals 2, and then F, which we really didn't even talk about because those are the really large elements that sit at the bottom of the periodic table. That would correspond to a value of L equals 3. Okay. There are kind of rules for if, given a value of n, L can be any integer from 0 to n minus 1. So there's sort of rules for, given a principal quantum number, what values of angular momentum quantum number are allowed. Again, anywhere from 0 to n minus 1. So if n equals 1, the only L value that's allowed is L equals 0, right? So when we had a 1s orbital, notice we didn't have a 1p orbital, or a 1d orbital, or a 1f orbital. That's because of these rules here. So likewise, when n equals 2, you can have L, again, be anywhere from 0 to n minus 1, which means anywhere from 0 to 1. And again, think about it. When we're talking about the principal quantum numbers of 2, we had a 2s and a 2p, but there was no such thing as a 2d. Okay, or likewise, when n equals 3, it can be 0, 1, or 2, which means that we would have to be up at n equals 4 to be able to have L equal to a value of 3, or be talking about an f orbital. Again, we're sort of going to stick to the lower level of, or the upper part of the periodic table, so let's not go too much into that. But anyways, yes, those are the different values that are allowed. So this is sort of this rule for what the allowed values for L are. M sub L. So we've actually already talked about this, but we just very much so didn't talk about it in the same context. The magnetic quantum number corresponds to the orientation of those orbitals. And it can take on a value from negative L to L. Okay, so let's say that we were talking about the 2p orbitals. The 2p orbital. In the language of our quantum numbers, this would be a principal quantum number equals to 2. Our angular momentum quantum number would be 1, right? Remember this correspondence here. S is 0, P is 1, D is 2, F is 3. So this would correspond to L equals 1. And M sub L can take on any value from negative L to L. So that would be a value of negative 1, 0, or 1. There are 3 possible M sub L values. And those correspond to those different orientations of those p orbitals that we already talked about, of those p sublevels that we already talked about, right? So again, they had these different orientations. Now we're putting these numbers on them. So this would be M sub L equals negative 1 would correspond to this particular sublevel. M sub L equals 0 would correspond to this one. And M sub L equals positive 1 or 1 would correspond to this orientation. Okay. Let's just real quick go back and do this for the D's as well. So, right, these we said were all these different D orbitals that we could, or D sublevels that we could have. If we look on our chart, whoops, we see that the 3D is the smallest D orbital, right? So if we were talking about 3D, in the world of our quantum numbers, this would be a principal quantum number equals 3, an angular momentum quantum number equals 2, and then M sub L, again, can take on any value from negative L to L. So this would be negative 2, negative 1, 0, 1, and 2. Notice that we have 5 different M sub L values, 5 different magnetic quantum numbers. Each one of those corresponds to our different orientations. All right, so we've kind of already been talking about it, but not really, sort of putting it in different words. But each one of these corresponds to a different orientation. And we know that 2 electrons can fit in each one of these sublevels. Okay, so going back to our little box here, let's just note we've already sort of been talking about, we talked about these electron configurations before these guys, as well as the diagrams. If I want to pick 3p here, 3p in the language of our quantum numbers corresponds to n equals 3, a principal quantum number of 3, L equals 1, and M sub L could equal negative 1, 0, or positive 1. Right? Those were those 3 different possible values. And again, each one of those corresponds to those different orientations of those p. So in the language of our orbital diagrams, each M sub L corresponds to one of these boxes. right? When we draw one of these boxes, really what we're doing is indicating a different M sub L value or magnetic quantum number value. So we could go through and label these with the M sub L values. This box would be -1, this box would be 0, and this box would be +1. What if I wanted to do the same thing with my 3s orbital? Then n would equal 3 still talking about that principal quantum number of 3. L would equal 0 for an s orbital, which means that the only possible value for M sub L is 0. So I only have one, and that checks with what we've been drawing all along, right? We've only been drawing one possible box for our s orbitals, so those correspond to the M sub L values of 0, right? So I could do the same thing here. So another P. I have a D on here. Yep. So for the 3D, I again have n equals 3. L now equals 2, which means that M sub L can be -2, -1, 0, 1, or 2. So if I wanted to go in and label these boxes here, -2, -1, 0, 1, or 2. Okay, so then notice how if I give you a 3-digit combination of N, L, and M sub L, a principal quantum number, an angular momentum quantum number, and a magnetic quantum number, it would correspond to a particular box on this diagram. So for example, let's say that I said N equals 2, L equals 1, and M sub L equals 1. Which box would I be talking about that corresponds to this quantum number, this 3-digit quantum number here? All right, so first of all, if N equals 2, that means I'm talking about one of those. L equals 1, what shape does that correspond to? That would be a p orbital. So I know I'm talking about my 2p. And then lastly, the M sub L equals 1. I'm specifically talking about this box right here. Okay, so these quantum numbers are kind of like the address of an electron. They tell you where it lives. These 3 digits, if I'm giving you 3 digits, I'm specifying a particular sublevel, which we know can fit maximum 2 electrons. So likewise, if I wanted to say N equals 3, L equals 0, M sub L equals 0. So this was this red example, this blue example. Which box am I specifically talking about? That would be this one here. What if I said N equals 3, L equals 2, and M sub L equals -1? What would I be talking about? Which box? All right, in this particular example of argon, it's empty, but I would be talking about this box right here. So again, if I'm giving you those 3 quantum numbers, the principal, the angular momentum, and the magnetic, I'm sort of giving you the address that could house maximum 2 electrons. Okay. Cool. So, I mean, this just sort of summarizes all that. Again, the key things to remember here is the principal quantum number N is the size of that orbital. The angular momentum quantum number L is the shape of that orbital. And the M sub L is the magnetic quantum number, which is the orientation. And importantly, the number of possible MLs equals the number of sublevels, right? So 1 for S, 3 for P, 5 for D. Cool. And then this is actually kind of a nice little diagram here that shows you for a given value of angular momentum quantum number L, what are the different M sub L values that are allowed, right? So this would be the S orbitals, this would be P orbitals. So now there's 3 values corresponding to those. These are the d orbitals. There are 5 values corresponding to those. And we didn't even really talk about them, but these are actually the f orbitals. You can see that now they're even more complicated looking shapes. And as we would expect, considering that f corresponds to an angular momentum quantum numbers of 3, that means that we have 7 possible magnetic quantum numbers, going from -3 to +3. And again, what is each one of these doing? They're corresponding to a different orientation of those sublevels. Okay. So now let's sort of just see, based on the rules that we've learned, this is one of the things I could ask you is this designation actually legal here? So 1p, is there such thing as a 1p orbital? Well, what we could do is translate this into our quantum numbers and make sure that they obey the right rules. So this would be n equals 1 and L equals 1. That's not possible because remember the maximum value for L is n minus 1, or in this case, 0. So there's no such thing as a 1p orbital. What about 2s? That would correspond to n equals 2 and L equals 0. That's legit. So then the second part of this question is how many atomic orbital sublevels correspond to each orbital? So how many different m sub L values do I have? Remember, those go from -L to +L. So in this case, I would just have 1 because that one m sub L value. 3f. Now I have n equals 3 and L equals 3. This is again not allowed. No such thing as a 3f orbital. Because again, L is maximally n minus 1. So if we're talking about an n equals 3, that means L is maximally 2. And so then lastly, 3D, well, this is n equals 3 and L equals 2. So that is allowed. And then how many different sublevels correspond to a 3D? Those would be m sub L equals -2, -1, 0, 1, and 2. So there would be 5 sublevels. Okay. All right, so there's a fourth quantum number that we can talk about, and that is spin. We talked about this a little bit. Electrons, it turns out, so electrons are kind of weird, but it turns out that they have a sort of angular momentum quantity associated with them that we call spin. And so how researchers kind of think about this is that electrons are spinning around like a top at all times. As they're moving around through the atom, as they're trapped within their orbital, they're also spinning around in a particular direction. And there are exactly 2 different directions that it could spin. There's nothing in between. It's either spinning what we call spin up, or spin down. Okay, and again, there's like no middle ground. It's either spin up or spin down. Typically when we're filling in our boxes, the first arrow we do pointed up and the second one has to then be pointed down. So we're going to now introduce a last quantum number here. We've already been over the principle, the angular momentum, and the magnetic. Our last one is called the spin quantum number. It corresponds to the spin of an electron, and that has one of 2 possible values. -1/2 for spin down, so that is for spin down would be -1/2, and then spin up would correspond to +1/2. So these are the only 2 values that are allowed for your spin quantum number. So that means going back to our electron configuration diagram, our orbital diagram, if I were to give you a combination of 4 quantum numbers, remember 3 specified a sublevel, As soon as I add that fourth one and I specify a spin, now I'm talking about a particular electron in that diagram. Okay, so going back here, if I wanted to describe this particular electron here, that would correspond to, so 3p, that means n equals 3, L equals 1. What would be the m sub L value of this box? Remember, there are 3 different ones, and they would go from -1, 0, and 1. So in this case, the m sub L, the magnetic quantum number, would be -1. And this particular electron that I highlighted is spin down. So that means the m sub S value would be equal to -1/2. All right, so this 3, 1, -1, -1/2 is the 4-digit quantum number address of that particular electron that I've highlighted in blue. Okay, so this is these quantum numbers. Again, you can think about them as an address of an electron. You'll be able to identify on your chart this particular electron has this configuration, or I could do sort of the opposite and say, find me the electron that has the quantum number address to 1, 1, +1/2. What would that correspond to? All right, so right off the bat, n equals 2, L equals 1. This would correspond to a 2p orbital. So I'm somewhere in here. M sub L equals 1. Well, again, if I'm going to label my box as -1, 0, and 1, now I know I'm talking about this last box here. And then +1/2 means I'm specifically referring to this spin up electron. All right, but those are our quantum numbers. Again, 3 of them will just specify one of your boxes on your orbital diagram. A 4th one, you can actually point to a particular electron.